Welcome to DAR Tutors for online and home tuition. In this video, we will cover the fundamental concepts of straight lines, a core topic in the IB Mathematics, Applications and Interpretation Higher Level Curriculum. Our focus will be on lines in the Cartesian plane, graphing straight lines, understanding perpendicular bisectors, and solving simultaneous equations. Let's begin with a practical application to set the context. Consider a town with two hospitals, located at coordinates A, -3, -2, and B, 2, 4. Grid units are in kilometers. The question is, how do we determine which hospital is closer to any given emergency location? Visualizing this on a Cartesian plane helps us understand the geometry of the problem. This problem will lead us to the concept of the perpendicular bisector, a line that defines all points equidistant from the two hospitals. We will return to solve this problem later in the video. We'll start by reviewing the basics of lines in the Cartesian plane. By the end of this scene, you will be able to find the gradient and intercept of a line and write its equation in point gradient form. First, the x-intercept is where a line crosses the x-axis, and the y-intercept is where it crosses the y-axis. The gradient, often denoted by m, measures the steepness of the line. You can find it using any 2 points on the line, x1, y1, and x2, y2. The formula is rise over run, or y2 minus y1 divided by x2 minus x1. Furthermore, there are two key properties for parallel and perpendicular lines. Parallel lines are lines with the exact same gradient. Perpendicular lines intersect at a 90-degree angle, and their gradients are negative reciprocals of each other. This means if one gradient is m, the perpendicular gradient is -1 over m. Now, let's look at how to write the equation of a line. The most versatile form is the point gradient form. It is derived directly from the gradient formula. If you know the gradient m and a single point x1, y1, you can write the line's equation as y minus y1 equals m times the quantity x minus x1. Let's work through an example to solidify this. Find the equation of a line with a gradient of -3 that passes through the point 4, -5. Here, our gradient m is -3, x1 is 4, and y1 is -5. Substituting these into the point gradient form gives y minus -5 equals -3 times x minus 4. Simplifying, we get y plus 5 equals -3x plus 12. Subtracting 5 from both sides, the equation is y equals -3x plus 7. This is the equation of the line. So we've reviewed how to find the gradient and intercepts, learned the point gradient form, and applied it to find a line's equation. Now let's explore the other common forms of a linear equation. By the end of this section, you will be able to convert between these forms and explain the significance of the general form. The gradient-intercept form, y equals mx plus c, is probably the most familiar. The gradient is m, and the y-intercept is c. The equation we found in the last example, y equals -3x plus 7, is in this form, so its y-intercept is 7. Next is the general form, ax plus by equals d. This form has a significant advantage. It can represent all lines, including vertical lines, which have an undefined gradient. For a vertical line like x equals 1, we can write it as 1x plus dy equals 1, showing its gradient is undefined. In IB exams, you may also see a similar form. The form ax plus by plus d equals 0 is equivalent to the general form. You simply move the constant d to the left side of the equation. Let's practice converting between these forms. First, write y equals -2 3x plus 2 in general form. To eliminate the fraction, we multiply the entire equation by 3. This gives 3y equals -2x plus 6. Then we rearrange to get all terms involving x and y on one side, which gives the general form. 2x plus 3ei equals 6. Second, write 3x minus 4y equals -2 in gradient-intercept form. We need to isolate the y term. Subtracting 3x gives -4y equals -3x minus 2. Dividing everything by -4 gives y equals -3x over -4. Which simplifies to y equals 3 so 6 plus 1/2. We have successfully converted to y equals mx plus c. We have now reviewed the different forms of linear equations and practiced converting them. We can now solve the opening problem we introduced at the beginning of the video. The goal is to find the perpendicular bisector of the line segment connecting the two hospitals. Let's first recap the problem. Hospitals are at A, -3, -2, and B, 2, 4. The ambulance is sent from the nearest hospital. We need to find the equation of the line that defines the boundary between the two service areas. This boundary is the perpendicular bisector of the line segment AB. A perpendicular bisector is a line that cuts another line segment exactly in half at its midpoint, and does so at a perfect right angle. Every point on the perpendicular bisector is equidistant from the two endpoints. This is exactly what we need to solve our problem. Here's the plan. We'll start by finding the midpoint of segment AB. Then we'll calculate the gradient of the line. Using that, we'll find the perpendicular gradient. Finally, we'll use the point gradient form to write the equation of the bisector. Step 1. Find the midpoint. The midpoint formula is the average of the x-coordinates and the average of the y-coordinates. Applying it, the midpoint is at -1/2, 1. Step 2. Find the gradient of AB. Using our points, the gradient m sub AB is 6/5. Step 3. Find the perpendicular gradient. The perpendicular gradient m perpendicular is the negative reciprocal of m sub AB. So m perpendicular is -5/6. Step 4. Find the equation of the perpendicular bisector. We use the midpoint m, -1/2, 1, and the perpendicular gradient m perpendicular equals -5/6 in the point gradient form. Rearranging this equation, we can write it in general form. 10x plus 12y equals 7. This is the boundary line. Any emergency on this side of the line, say at P, is closer to A. Any emergency on the other side, like at Q, is closer to B. This line geometrically defines the two service areas. We have now solved the opening problem by finding the perpendicular bisector and understanding its properties. Our next topic is simultaneous equations. By the end of this scene, you will be able to solve a system of two linear equations in two variables, using two algebraic methods, substitution and elimination. Geometrically, solving a system of two linear equations means finding the point where their two lines intersect on a graph. Let's first tackle the substitution method. This method works best when one of the variables is already isolated or can be easily isolated. Consider the system, y equals x minus 3 and 2x plus 3 equals 16. The first equation already gives us an expression for y. Step 1. Substitute the expression for y from the first equation into the second equation. This gives us an equation with only one variable, x. Step 2. Solve the resulting equation for x. Distributing the 3 gives 2x plus 3x minus 9 equals 16. Combining like terms and rearranging, we find that x equals 5. Step 3. Substitute the value of x back into one of the original equations to find y. Using the first equation, y equals 5 minus 3, so y equals 2. Our solution is the point, 5, 2. To be thorough, we always check our answer by substituting both values into the second equation. 2 times 5 plus 3 times 2 equals 10 plus 6, which is 10. The solution is correct. Now, let's explore the elimination method. The elimination method is ideal when variables are aligned, and we can easily create opposite coefficients. Consider the system. 3x plus 4y equals 2, and 2x minus 3y equals 7. Notice that none of the coefficients are easy to eliminate as they are. The key idea is to multiply one or both equations by a constant to make the coefficients of one variable opposites. Let's choose to eliminate y. We can find the least common multiple of 4 and 3, which is 12. So we'll multiply the first equation by 3 and the second by 4. This gives us 9x plus 12y equals 6, and 8x minus 12y equals 28. Notice the positive 12y and negative 12v are opposites. Step 2. Add the two new equations together. The y terms cancel out, leaving us with 17x equals 34. Solving for x, we find x equals 2. Step 3. Substitute x equals 2 back into one of the original equations. Using the first one, we get 6 plus 4i equals 2. Solving for y, we find y equals negative 1. The solution is 2, 1. We can again check our answer. We have successfully solved two systems of equations using both substitution and elimination. We have reached the 10-minute mark. If you find this video helpful and are looking for more personalized guidance, consider contacting DAR Tutors. DAR Tutors offers expert tuition in the IB A-Level and IGCSE curricula, providing tailored support to help you achieve your academic goals. Now let's continue with our lesson. Now let's consider a special case in solving simultaneous equations. What happens when there is no unique solution? In this scene, you will learn to identify systems with no solution or infinitely many solutions and interpret them geometrically. Geometrically, there are three possibilities for two lines in a plane. They can intersect at one unique point, which is our unique solution case. Or they could be parallel and never intersect, meaning there is no solution. Finally, the two equations could actually represent the exact same line, resulting in an infinite number of solutions. We can identify these cases algebraically. It all comes down to the gradients of the lines. For a system to have a unique solution, the lines must intersect, which means they cannot be parallel. Therefore, their gradients must be different. For a system to have no solution, the lines must be parallel and distinct. This means they must have the same gradient but different y-intercepts. For a system to have infinitely many solutions, the lines must be identical or coincident. They have the same gradient and the same y-intercept. Let's use this knowledge to solve an IB-style problem. We are given a system with a parameter m and asked to find the value of m, for which there is no unique solution. Part A asks for the gradients. For the first equation, 3x minus 2y equals 12, we can rearrange it into gradient-intercept form. This gives y equals 3 to 2x minus 6, so its gradient is 3 to 2. The second equation, y equals mx minus 6, is already in gradient-intercept form, and its gradient is m. Part B asks for the value of m where there is no unique solution. This means we are looking for the no solution or infinitely many solutions case. In both of these cases, the lines must have the same gradient. Therefore, the gradient of the second line, m, must be equal to the gradient of the first line, 3 to 2. So m equals 3 to 2. Let's check which specific case this leads to. When m is 3, 2, the second equation becomes y equals 3, 2 cx minus c. This is exactly the same equation as the first line. Thus, these are coincident lines, and there are infinitely many solutions. We have successfully found the value of m. We have now learned to distinguish between different types of systems of linear equations based on their gradients. A very common type of problem in IB involves finding the area of a triangle formed by lines. By the end of this scene, you will be able to calculate the area of such a triangle. The strategy is always the same. Find the vertices of the triangle by solving simultaneous equations, and then use the area formula. The problem asks for the area of the triangle defined by three lines. We need to find the three vertices first. Each vertex is the intersection point of two of the lines. Let's find the first vertex, where lines 1 and 2 intersect. Substituting y equals x plus 2 into x plus y equals 9, we get x plus 2 equals 9. This gives 2x equals 7, so x equals 3.5. Substituting back, y equals 5.5. The first vertex is 3.5, 5.5. Now for the second vertex, the intersection of lines 1 and 3. This one is easy. We substitute y equals 2 directly into y equals x plus 2. This gives 2 equals x plus 2, which means x equals 0. The second vertex is 0, 2. And finally, the third vertex, the intersection of lines 2 and 3. We substitute I equals 2 into x plus y equals 9, which gives x plus 2 equals 9. This means x equals 7. The third vertex is 7, 2. We have our three vertices, 3.5, 5.5, 0, 2, and 7, 2. Now we find the area. The base of our triangle is the distance between the two vertices with the same y-coordinate. This is the distance between 2 and 7.2, which is 7 units. The height is the vertical distance from the third vertex, 3.5, 5.5, down to the line y equals 2. This distance is 3.5 units. Using the area formula, area equals 1/2 base times height. We get 1/2 times 7 times 3.5. This simplifies to 12.25 square units. Remember to always include units in your answer. We have now learned how to find the area of a triangle by identifying its vertices and using the area formula. A more advanced IB problem involves 3 non-collinear points. By the end of this scene, you will be able to find the center and radius of the circle passing through 3 given points. This problem combines our knowledge of perpendicular bisectors and simultaneous equations. The key principle here is that every point on a circle is equidistant from the center. This means the center of the circle must lie on the perpendicular bisector of every chord of the circle. A chord is a line segment connecting any 2 points on the circle. So if we have 3 points A, B, and C, the center of the circle must lie on the perpendicular bisector of the chord AB and also on the perpendicular bisector of the chord BC. The center is simply the intersection of these 2 lines. Let's apply this to an example. We want to find the center of the circle that passes through points A, 1, 2, B, 4, 5, and C, 2, 1. First, we'll find the equation of the perpendicular bisector of AB. The midpoint of AB is 2.5, 3.5, and the gradient of AB is 1. So the perpendicular gradient is 1. Using point gradient form and simplifying, we get the equation 2y equals 2x plus 12 or y equals x plus 6. Next, let's find the equation of the perpendicular bisector of BC. The midpoint of BC is 3, 2, and the gradient of BC is 6, so the perpendicular gradient is 1, 6. The equation simplifies to 6y equals x plus 9. The center of the circle is the intersection of these 2 lines. We need to solve their equations simultaneously. Let's use substitution. Substitute e equals negative x plus 6 into the second equation. This gives 3 times negative x plus 6 equals negative x plus 9. Solving for x, we find x equals 4.5. Substituting back, y equals 1.5. So the center of our circle is 4.5, 1.5. Now that we have the center, we can find the radius. The radius is the distance from the center to any of the 3 points. Let's use point A. We use the distance formula. The distance squared is 3.5 squared plus negative 0.5 squared, which is 12.5. So the radius is the square root of 12.5, which is approximately 3.54 units. We have now completed our coverage of Chapter 1, Straight Lines. We started with the basics of points and gradients and built up to solving complex problems involving perpendicular bisectors and simultaneous equations. Now it's time to test your understanding with some IB-style practice questions. Question 1 asks for the general form of a line with a given gradient and point. Press pause to attempt the question. Here is the solution. We start with the point gradient form, substitute our values, multiply by 4 to clear the fraction, and rearrange to the required form. The final answer is 3x plus 4y minus 17 equals 0. Question 2 gives us an equation in general form and asks for the gradient. Again, pause the video and give it a try. To find the gradient, we must rearrange the equation into gradient-intercept form, y equals mx plus c. Isolating y, we find that 2y equals 6x plus 7, so y equals 3x plus 7 and 2. The gradient is 3. Question 3 is an application problem. Take a moment to read and solve it. This is not a linear equation, but a quadratic. The problem tests your ability to adapt your knowledge. For part A, the ball is thrown when t equals 0. H is 3 meters. For part B, the time at maximum height for a quadratic ax squared plus bx plus c is given by negative b over 2a. This is 20 divided by 10, or 2 seconds. For part C, we substitute t equals 2 into the equation, which gives a maximum height of 23 meters. Question 4 asks for the equation of a perpendicular bisector. You can do this. Pause the video to work through it. Here's the solution. The midpoint is at 6, or 1. The gradient of AB is negative 2 to 3, so the perpendicular gradient is 3 to 2. Using point gradient form, the equation is y plus 1 equals 3/2 times x minus 6, which simplifies to 2y equals 3x minus 20. Finally, Question 5 involves a system with a parameter a. Determine the value of a that leads to infinitely many solutions. Infinitely many solutions occur when the lines are identical. We can achieve this by making their equations multiples of each other. The second equation, 4x minus 2y equals 10, can be divided by 2 to get 2x minus y equals 5. This new equation is identical to the first if a equals 2. So, a equals 2. We hope these practice questions helped reinforce your understanding. To recap, we have covered the key concepts of straight lines in the Cartesian plane. We reviewed the different forms of linear equations, learned how to graph them, and how to find perpendicular bisectors. We also explored how to solve systems of linear equations using both algebraic and graphical methods, and how to interpret cases with no solution or infinitely many solutions. We also saw how these concepts are applied in IB-style problems, such as finding areas of triangles and locating the center of a circle. Mastering these foundational skills will be crucial as you progress in the IB mathematics. Applications and Interpretation Higher-Level Curriculum. Thank you for watching this video from DAR Tutors. If you need further assistance or expert tuition, please visit our website at dartutors.com. Goodbye for now.